Next speaker is GREGORY MIERMONT. Speak about 25 ans après, la bijection continue. The bijection goes on.
Yes, so okay.
It's from Alexandre Dumas, I presume.
Yes, yeah, that's a good point. Yes, so I wanted to give a slightly fancy name because I have the last talk in the day. So 25 ans, so 25 years. It's a bit arbitrary, but the bijection, of course, refers to the class of bijections between trees and maps that we've heard about in the morning. And well, they actually were introduced about 45 years before now, but they were really revived through the work by by the star of today and his collaborators, and of course Gilles Shaeffer. So thanks a lot for the invitation to speak here. So it's about joint work with Omer Angel, Brett Kolesnik, and Emmanuel Jacob. And it's a real pleasure to be here to celebrate Emmanuel. So as Jeremy was saying this morning, we've known Emmanuel for quite a long time. I met him at the occasion of a seminar on random maps that was held in Orsay starting around 2005. And it was really fantastic because it was gathering together probabilists, theoretical physicists, combinatorialists, and there was for a long time of a ping pong between these persons. We had new bijections. We used them in in context of probability, random maps, physics models, and so on, and yeah, this ping pong continued for quite a bit of time, and more recently, I viewed Emmanuel as someone who is reluctant to travel, but in fact, in the recent years when we had meetings, you were saying, well, okay, maybe I don't want to travel too much and so on. But this morning, I learned that actually you traveled quite a lot, drove nice cars, and in fact, it seems to me that when you travel, some phase transition happens. For instance, Tintin becomes a neat. You wear fancy hats, and the last time actually I remember you traveling was you coming to Lyon, and it actually for me it was a big phase transition because we came to the other side of the ping pong table and become a working desk, and I'm really glad that we have this ongoing collaboration. So as I said, putting together probability, theoretical physics, and combinatorics. So these talks will be basically about none of these topics. And let me start in a bit of provocative way. So of course, everybody knows the Corey-Vauquelin-Shaeffer bijection and its extension by Bouttier-Di Francesco-Guitter, because it's the most cited paper by Emmanuel. So you should know it. If you don't, you have to read the paper. And after this talk, you have no excuse because I will present it. So usually it is presented as a mapping from taking well-labeled plane trees, whatever this means, to pointed plane quadrangulations. And the reason why it's presented in this way is because it has a nice counterpart in the continuum, as I will stress later. So how does it work? So first we start from a well-labeled tree. So it just means a tree embedded in the plane, like this, plane tree, with labels on the vertices, and with a certain rule that the difference of the labels along an edge should be at most 1 in absolute value. Okay? So here you see that, for instance, the path going from bottom to top is 0, -1, -1, 0. You only make steps of 0, +1, or -1. Okay, and now what we do is we go around the tree in contour order, and we link the consecutive corners that we encounter to their successors, which means the next available corner of lesser label. So first of all, the corners with minimal label, -2 on this picture, will obviously not have a successor. So we just build one from scratch. We put an extra vertex, which is supposed to be the successor of the corners which have no successors. And then when you have done that, then you can indeed perform this operation in a non-crossing fashion. So for instance, you see that the root corner here is linked to the next vertex with label, next corner, let's say, of label -1. This corner incident to this vertex is linked to the next 0, this 0 to the next -1, this -1 to the next -2, and so on and so forth. And the very nice property of this bijection is that it yields a quadrangulation which is naturally pointed at the vertex that you have added in the beginning. And you can also root this quadrangulation if the tree was rooted in the first place. For instance, if you consider this bottom vertex as the root of the tree, you can also root the quadrangulation. And so that's the Corey-Vauquelin and Shaeffer bijection, or mapping from well-labeled trees to pointed and rooted quadrangulations. And one other nice thing is that, in the last picture, I removed the labels that were appearing in the beginning, because you can, in fact, recover those labels by taking the graph distances from V star. So the graph distance is just the minimal number of edges you need to go to V star. And so, for instance, this one will have label 0, these two ones will have label 1, 2, and so on. And then you shift all those labels by the label of the root, and you get back the labels. Okay, so that's the very nice property of the bijection. Now, the inverse mapping is also very interesting, of course. And starting from this time pointed, possibly rooted quadrangulation, essentially what you have to do is to determine a geodesic spanning tree in the map. And you can do it as follows. So, of course, what does it mean, the geodesic spanning tree? I mean, the geodesics, the path in the map will, of course, cross each other. They do not form a tree. But when you have several geodesics and, arriving at a vertex, you will have somehow to lift ambiguities and to separate them to make a tree. So how does one do that? First of all, I'm considering a big map, but I'm focusing only on one particular vertex, which is at distance L from V star, okay, the pointed vertex. And the orientation just means that if I go away, if I go in this direction, I will go to vertices that are farther away from V star, okay, so I go just from L to L plus 1s, and if I have an incoming edge, it means that I arrive from a vertex which is closer to V star, like L minus 1, okay? And now we interpret each of these vertices as a British roundabout, okay, with cars arriving all at the same time L at the roundabout and trying to turn left, okay? They try to turn left, but of course they will have to yield, okay? For instance, those arriving here can turn left and leave the roundabout here, but they have to yield to the car that arrives at the same time here. So what it does on this picture is that you can just separate the various geodesic paths coming to this vertex V with label L, and you can construct a plane tree whose branches correspond to the cars that must yield. So you put a branch that traverses the part of the roundabout which are not visited by the cars. And in this interpretation, you see that it is indeed the inverse construction of the Corey-Vauquelin-Shaeffer bijection. Okay, so this is why I put these branches in red. They correspond to the initial tree in red. And you see that within this interpretation, the internal vertices of the tree, they exactly correspond to vertices of the map from which you have several geodesic paths that go to V star. Okay? Because if you have only one such path, then it will mean that you have also only one red branch, which means that L is, this vertex is in fact a leaf of the tree. So that's one interpretation of, the initial tree we started from. Now, as I said before, the nice property of this bijection is that it has a nice continuum counterpart, which is very useful when one wants to consider scaling limits of maps. And this was indeed something that was quite developed in the, starting at the seminar carte aléatoire in Orsay for some time. And here is how it goes. So if you want to understand the statistics of a large random quadrangulation, well, you just start from a large, well-labeled tree, you take an uniformly at random, and then you try in the end to apply the Curie-Vauquelin-Shaeffer or the Bouttier-Di Francesco-Guitter bijection. So start from Tn and Ln, a uniformly random, well-labeled rooted plane tree with n edges, say. Let's think of n as being large. And what we want to do is, first of all, describe this tree through a pair of easier objects, which are the contour and label process. So the contour is just going around the tree starting from the root and recording the successive heights of the vertices. Okay? It's just the representation of a tree by a lattice path. And Ln of I will correspond to the labels of the vertices that you encounter. I didn't draw Ln of I on this picture. I just showed the contour order. And then, well, I think starting from Chassin and Shaeffer, the paper that was mentioned this morning, one of the first, probably the first paper about the combinatorial understanding of distances in quadrangulations. Well, this contour and label process, which are random functions, they actually converge in the limit when you rescale in the proper way. So you have to rescale the contour process in a diffusive fashion and the label process by the square root of the square root of n to a certain limiting objects, which I denote by E and capital Z, where E is a standard Brownian motion excursion. So it's really the continuum analog of a lattice path, which remains an excursion of a lattice path. So I've drawn a picture here. And Z is conditionally on the excursion a centered Gaussian process with a certain covariance function, which is maybe a complicated way to say that the process Z along the branches of the tree that is coded by the excursion E performs Brownian motion, just in the same way that the labels along the discrete tree were performing random walks with steps of +1, -1, and 0. And the property is that if, the property of this covariance function is that if you go in different branches, then the Brownian increments become independent. Okay, so it's really Brownian motion indexed by a certain continuum object, which is the tree coded by the excursion E. I will come back to that in a minute. So, in the world of labeled trees, so this has a name. This is essentially the Brownian snake of Le Gall. In the context of labeled trees, we understand very well the scaling limits of these random objects. And the question is, can you pass to the limit the continuum? The Curie-Vauquelin and Shaeffer bijection. So let's try to do it. You can actually do that. So let us be a bit more formal. So what we are going to do is we are going to define distance functions associated with the process E and Z by these formulas. So in words, maybe the distance between the points of the tree visited at time S and T will be equal to the sum of the lengths of this red path and the length of this green path, which means exactly that in order to go from this vertex to that vertex, you have to go to a most recent common ancestor and then to go back up. Okay, and this is exactly what is written in this definition. And for Z, you have a slightly different definition, essentially because Z is a process that takes both positive and negative values, and that you have two ways to travel from S to T, going in a circle. You can go either from S to T or from T to S, going passing through one. Okay, this is just maybe a bit technical definition, but what it says, this tree distance is for Z corresponds exactly to the distance in the geodesic tree that I described when I defined the Curie-Vauquelin and Shaeffer bijection, namely going from two vertices of the tree, you go back to the root, which is the vertex of the distinguished point, which is the vertex of minimum label, and you do that from two different points until the geodesics merge. And the length of the path that you obtain here is the distance between A and B when you restrict yourself to this geodesic tree sitting inside the map. So you have two distances that you should interpret as continuum tree distances defined on the interval 0, 1. And you can actually define two mathematical objects which are called real trees by taking a quotient. So you just identify the points of 0, 1 which are at distance 0. So it means, for instance, on this picture, that the points along the blue line here should be all identified together. And in doing so, you obtain a tree. In fact, you obtain two trees, one associated with E and one associated with Z. And in order to pass the Curie-Vauquelin-Shaeffer bijection to the limit, well, you should start from the geodesic tree and remember that the several points in these geodesic trees were identified in the first place. And they were identified exactly because they were corresponding to the same point of the tree, of the well-labeled tree we started from. So formally, you define a distance, which is called the Brownian sphere distance, by taking a quotient of the geodesic tree distance dz, which is if you want, the maximal possible distance, which is at the same time less than dz, and which satisfies that 2 points identified for the tree distance with a primal tree should be at distance 0 in the end. So this is the formal definition here, but it's not so important. You really glue the geodesic tree associated with Z to the tree associated with E. And that's really the continuum analog of the Curie-Vauquelin and the Shaeffer bijection. And the object that is called the Brownian sphere itself, it's again defined as a quotient space. This capital D here is not a true metric because it does satisfy the triangle inequality, but it identifies some points which are different. So you just take a quotient of 0, 1 by the points that are identified together, and you obtain a metric space, which is called the Brownian sphere, and which can be shown, for instance, to be indeed the limit of uniformly chosen quadrangulations with properly rescaled distances. But I'm not going to focus about that. I'm going to focus entirely about this continuum space here. So first of all, this space, a little bit as in the discrete bijection, you can further decorate it, for instance, by adding marked points. So these two marked points will correspond to the root of the tree, of the well-labeled tree you started from. So you just take the image of the point 0 by the projection from 0, 1 to x. And a second point is a distinguished point. Remember, the one which had the smallest possible label in the tree. So this is P of the argmin of the label process Z. And these form two naturally distinguished points in the space. And you also have, on top of it, a probability measure, sometimes called the area measure, which is the push forward of the Lebesgue measure by the projection from 0, 1 to x. So the Brownian sphere, so the Brownian sphere, you can view it as a metric space. I forgot actually to write the distance, but you have a metric space xd with two distinguished points and a measure. Now, the question is there a natural analog of the, is there a Curie-Vauquelin-Shaeffer or a Bouttier-Di Francesco-Guitter bijection in the continuum? Namely, this transformation, can you invert it? I mean, there is no particular strong motivation to this question. It's just out of pure curiosity. Is it actually possible if I just, I don't tell you what tree I started from, but I just give you the sphere. It's a slightly spiky object, so you don't hurt yourself. But if I give you this fractal sphere, can you recover the tree I started from? So in a sense, this is in fact a folklore result, because a theorem by Le Gall from 2010 says that you can actually view let's say the skeleton point of TE, namely the points that are really inside the tree, so formally such that TE minus this point becomes a disconnected set, so it's sometimes called the skeleton of the tree, can be viewed as the homeomorphic image of a geometric locus inside the Brownian map, the Brownian sphere, namely the set of points x from which there exists at least two geodesics from x to x1. So you have this geometric locus in the Brownian sphere, and this set of points is actually the homeomorphic image of the skeleton of the tree TE. So it's not really recovering everything, but at least you have presumably most of the tree. And on top of that, I said that the labels, they correspond to distances. So you can also recover the labels on top of the cut locus just by looking at distances parameterized by this homeomorphism. And okay, so once you have the skeleton of the tree and the distances, yeah. So I think the restaurant is at 7:30, so I have 2 hours, right? Okay. Right. Okay, I might be a little late. Okay. Yeah. Okay, so once you have done that, you see that you don't have all the information. For instance, you do have an embedded tree, but you still need to understand a kind of planar order if you want to do a contour along this tree. And maybe you also need to understand what are the lengths of the path in this tree. And maybe I will go a bit quickly on that. But once you have the labels around the tree, somehow you have a Brownian motion, which is the Z labels around this vertex, along the line, but maybe up to parametrization. But the point is that if I give you a Brownian motion and hide the parametrization, the time parametrization that I've used, you can in fact recover it by taking a kind of a quadratic variation. This is something quite standard. So if I give you a Brownian motion, but I don't tell you how I parameterized it, you can in fact find the parametrization. So, well, presumably you can indeed invert the Curie-Vauquelin and Shaeffer bijection. The problem is that can you actually perform that as a measurable function of the metric space? And this is this is quite a different question in a sense, and this is a question I want to answer here. So first of all, you have to be a bit more formal if you want to talk about measurable functions. First of all, you have to define this continuum Curie-Vauquelin-Shaeffer mapping as a measurable function from some space to some other space. And the natural way to do that is to generally talk about pairs of functions, let's say f and g, okay, and associate with them, so you have two continuous functions, and you associate with them two real trees, exactly as was done for E and Z. And you can also define a quotient pseudo-distance by taking the quotient of dg by the set of points identified by f. You can identify, you can add on top of that a measure which is a push forward of the Lebesgue measure on 0, 1, and two marked points exactly as for E and Z, but you do it in a general setting. And the first remark is that in doing so, you do get a nice measurable, let's say, Borel mapping from the set of these pairs of functions to some set, to some space, which is called the Gromov-Hausdorff-Prokhorov space of marked isometric classes of compact metric measure spaces. This is just a way to make sense of this of these objects up to isometry. And in particular, the Brownian sphere, you can view that indeed as a measurable image of a random variable easy as before by this formal Curie-Vauquelin-Shaeffer mapping. Now, if you want to invert it, in fact, there is a very nice result from general measure theory, which is due to Luzin and Suslin around 1917, which says that if you have two nice spaces, standard Borel spaces, and a Borel set, and if you have a function f, which is Borel measurable, such that the restriction of f to a is injective, then in fact the image is a Borel, and f induces a Borel isomorphism between the two. That is, the inverse of f is also Borel measurable. So, okay, so you remember, from the class on measure theory that the image of a Borel set by a measurable function is not necessarily Borel, but when you have injections, then everything goes very, very nicely. So the message somehow is that bijections are nice also in the continuum world. So it says that if you can abstractly invert a mapping, then you can also do it concretely. Now you have a problem, which is that the formal CVS mapping that I introduced is actually not injective. Indeed, if you revert the time in both f and g, well, you get exactly the same space in the end. This is something that is very easy to see. The point is that this is essentially the only obstruction to injectivity, namely if you are able to recover the orientation of the processes f and g, then you get an injective path. And what you can do is you can recover this orientation by putting a little extra variable epsilon h, which is essentially saying whether the argmin of G is less than 1/2 or bigger than 1/2, and this allows you to say where this argmin was. Okay, I want to have maybe one word of conclusion. So essentially by stating a theorem, which is in a sense the continuum CVS bijection made formal. So there exists indeed an inverse to the previous mapping psi extended with this extra sign, which if you start from a marked Brownian sphere will give you the, if you apply phi and get somehow the label trees and reapply psi, you will get the sphere you started from. And if you start from the pair E and Z in the beginning and you apply this measurable map, you get the initial pair of functions that you started from. Right. So, okay, so maybe I can take questions.
Yes, so
very good question.
Good question.
Very good question. Okay, so the proof of this theorem essentially was, the one that I gave using the theorem by Le Gall and so on was essentially a complete proof, in fact. But, there is a nice discussion about this epsilon. What it says is that what you obtain is you recover the pair of functions, but up to the orientation. In fact, it corresponds exactly to the orientation. The Brownian sphere is indeed a topological sphere, so it can be given two natural orientations. If I give you the metric of the sphere, you cannot tell me what the orientation was. And the natural thing to do would say, okay, just choose the orientation uniformly at random by flipping a coin. The question is, can you do that in a measurable way? This is not completely clear, and this is exactly somehow what this theorem does. Okay? So first of all, you get that this mapping psi h and the orientation variable are independent with epsilon h uniform over -1 and 1. And indeed, if you change epsilon, then you just get the reverse of the mapping phi. Okay, so I would have to discuss a little more, and I don't have time. Why taking this random variable, why somehow orienting the functions f and g correspond actually to orienting the sphere, but it's done just by saying that these pairs of trees that are embedded in the map, they allow you to distinguish certain Jordan domains in the map. And once you have a Jordan domain, which is, let's say, circled by an oriented curve, orienting the sphere just amounts to saying what is the Jordan domain which is to the left and what is the one to the right. And this is exactly what the variable epsilon allows you to do. Okay. Something which is not completely satisfactory in this statement is that you start actually from an object which has more decorations. It has a measure and two marked points. And these marked points are very important because these are the points that allow you to say with respect to what you are considering the cut locus in the map. But the nice thing is that these points, you can also forget them. They just play the role of 2 points which are sampled uniformly according to the measure mu. And you can somehow get a version of this theorem just by taking the sphere and then sampling 2 points at random and then applying this inverse Corey-Vauquelin-Shaeffer bijection. And by another result by Le Gall, you can even get rid of the measure. Namely, the measure mu is in fact determined by the metric structure. And by another application of the Luzin-Suslin theorem, you say that once you know that abstractly the measure mu is determined by the metric structure, you know that there is a measurable map that will take the metric structure and cook for you the measured metric space. And now maybe in order to conclude, I want to say that the Luzin and Suslin theorem is, it's a purely theoretical tool, but I think it's good to have it in mind because it says that a measurable map that you can abstractly invert, it can also be inverted concretely. And in this case, we describe the continuum analog of the continuous Shaeffer, the Curie-Vauquelin-Shaeffer bijection, or let's say the Bouttier-Di Francesco-Guitter bijection with small faces. But in a sense, there should be also a related continuum Chapuis-Marcus-Shaeffer bijection in the context of Brownian surfaces, maybe in a higher genera, and maybe a continuum Bouttier-Di Francesco-Guitter bijection. I mean, the Bouttier-Di Francesco-Guitter bijection is useful when you want to consider maps with arbitrary phase degrees, and maybe it can also be used to invert, the stable maps with exponent alpha that we recently considered, introduced actually with Jean-François and recently considered in this work with Nicolas Curien and Armand Riera. Maybe a question is whether you have a single measurable map that works for every alpha. Anyway. And maybe also it's good to have in mind in some other contexts where you abstractly invert certain constructions like in LQG. Sorry for going over time, and thank you very much for your attention.
Okay.
Yeah, I'm done now.
Okay, thank you very much. Let's have some questions. Thank you for this very nice talk. Where is a cube? Yes.
You mentioned the stable maps. Do you have the same structure, geodesics, in the stable maps?
Yes, so the point is that you can also, how should I say that? You can also describe, so the stable maps, they are defined as a quotient of another kind of object which is called a loop tree. And this loop tree also corresponds to a certain, at least part of this object corresponds to a cut locus also. So in this context, the cut locus does not allow to recover the whole of the loop tree. So you have to come up with some different ideas. But for instance, you have, you still have properties of confluence of geodesics and properties like this. So I would expect that the situation is quite similar. But
more complicated, this is what you're saying?
So the point is that the cut locus, it's not completely clear that the cut locus allows to recover the loop tree that you somehow the tree structure. So in this context, it's not a tree structure anymore. So it's a slightly different object. It's not completely clear that you can rebuild everything from the cut locus. But I would expect that some variation of these arguments will still work. But it would be different. Yeah.
Another question? Yes.
Thank you for the assist. Thank you for your talk. At some point you said that the whole point of your theorem is basically to prove this the existence of this epsilon in a measurable way. So could you say a bit what it means for non-experts in probability?
It's not really a probabilistic statement. It's somehow what it says. Okay, what it does is that it selects for you an orientation of the sphere in a natural way. It's not the only one. I mean, you could have chosen maybe the epsilon in some other way. For instance, you can choose minus epsilon. Okay, this is a trivial one, but you could cook up some other possibilities. It's not canonical. The point is that somehow, if I give you an abstract sphere and I want to tell you choose an orientation of this sphere, it's not completely clear that you can select this choice in a measurable way, and this is exactly what we do.
Just to be clear, when you say in a measurable way, that's with respect to which measure?
Yeah. So, okay. So I had to go quickly through these things. There is no measure. In a sense, you have this abstract Curie-Vauquelin-Shaeffer mapping is a measurable map that goes from a certain space to some other space. And my claim is that the inverse of this map is also measurable. Okay? Now, the thing is that where the measure comes in is that you actually invert it on a space which is a full measure, you know, a set which is a full measure with respect to the objects of interest, which are the process E and Z and the Brownian map. So of course, what this operation does on metric spaces which somehow go outside of this support is meaningless in a sense. It does nothing interesting.
Thank you.
Okay, let me thank the speaker again.
Thank you.